Okay, welcome to Let's Get to the Marks. Going through electrophilic addition of alkenes, looking at the electrophilic addition of unsymmetrical alkenes to form a minor and a major product. All right, let's get into it. Let's go. The alkene 3-methyl pent-2-ene, we got the structural formula here, reacts with hydrogen bromide to form a 3-broma 3-methyl-pentane and 2-broma-methyl pentane, 2-broma 3-methyl pentane. The alkene 3-methyl pent-2-ene exists as E and Z stereoisomers. Draw the structure of Z3-methyl pent-2-ene. Okay, so when drawing these isomers, we want to first of all focus around the fact that they are EZ isomers, stereoisomers, and they're formed because there's no rotation around the double bond. The double bond is a planar area of the molecule, and there's no rotation around it. So that is my starting point for drawing a stereoisomer. Now it says pent-2-ene. So I know that this is the second carbon. I might make this one the second carbon. So I'm going to go ahead and add a carbon here. And this could be, I'm drawing a displayed formula here, but you could do this as a skeletal formula as it doesn't specify, got to be displayed, etc. So now how many more carbons do I need to make pent? So I know that that is carbon one, that is carbon two because it's pent-2-ene. So I'm calling this carbon one, carbon two. I need two more carbons in the main carbon chain. So I'm going to come off, say, down here and I'm going to go, and you're going to have to bear with me. I'm going to make adjustments later on. The whole point is that I'm going to show you the incorrect way first, and then I'm going to make adjustments before you start screaming and throwing things at the screen. All right. So now I have a pent chain, don't I? I have five carbons in a row, and I've got the double bond on carbon number two if that's carbon number one. Now we're told there's a methyl group coming off. So 3-methyl pent-2-ene. So I can put a methyl group coming off of carbon three. If that's carbon one, two, three, four, five, then this is where I'm going to put my methyl group. And lastly, but not least, I'm going to smash a hydrogen there. Now, this isn't necessarily right. I need to check. So what we need to check is that Z, what does Z mean? Z means Zusammen, which means sisters. So when you have, it means you should have two of the same group on one on either side of the double bond. Okay, now in order to be a Z or E isomer, each of these carbons, so each of these carbons should have a different group attached. So you see, I've got an ethyl group and a methyl group. That's fine. I've got a hydrogen and a methyl group. That's fine. But each carbon must have two different groups attached. You can't have an EZ isomer where you have a methyl group here and a methyl group there. That's impossible. You can't have an EZ isomer where you have a hydrogen coming off this carbon and a hydrogen coming off down below. Okay, they have to have two different groups attached. Now, because all four groups or the groups aren't identical in split into two easy pairs like chlorine atoms and hydrogen atoms, I've got to use the Chern or Kern-Ingold principles um, basically to work out what's high priority and low priority. Now, as it's sisters, I need to have both low priorities on one side and both high priorities on the other. Let's just check that. I'm going to start here and I'm going to call this, this is my first carbon. We could call this carbon A, right? Just for reference. And we could call this carbon B. So I'm looking at carbon A and I'm going to say, what have I got here? Hydrogen has an atomic number of one, so that is going to be my lower priority. And down here, this is my methyl group with a atomic number. The carbon atom on the methyl group has an atomic number of 12, so this is going to be my high priority. So I've got a low priority on that side of the double bond and a high priority on this side. Now let's go to carbon B and let's check this one. Right here, this has an atomic number of 12. Oops, this also has an atomic number of 12. What do you do when the atomic numbers are equal on the first atom? You go to the next atom attached. And if I go to the next atom attached here, it's a hydrogen. And so the next atom attached has an atomic number of 1. So this is going to be my low priority once again on this side. And why is that? Because here, the next atom attached is another carbon with an atomic number of 12. So what I can say here, or a methyl group. So what I can say here is this is high priority. And that means that this is a Z isomers. I've got sisters, two low priorities on that side and two high priority sisters on that side. So the sisters, when you have E antigen, it means opposite. If it was antigen, I would have my methyl group there and an ethyl group here. So I'd have like low and high across from each other. Um, they'd be opposite each other. I'd have like one high priority there and one high priority there. But so this methyl group would have to be up there and this hydrogen down here, and then that would be an E isomer. But this is a Z isomer. Anyway, I've over talked about that. But there we go, folks. That is how to do that one. Now you can do the skeletal formula for that. I'll put that up here. But shh. Right, let's move on. Okay, we're down to 7.2. Name and outline the mechanism for the formation of 3-bromor-3-methylpentane from this reaction of 3-methylpentoene with hydrogen bromide. Explain why more 3-bromor-3-methylpentane is formed in this reaction than 2-bromor-3-methylpentane. And this is worth 7 marks, so let's get into it. What I'm going to do here, you could explain this all in words, but you could also get sort of 5 out of the 7 marks from the diagram alone, or you could probably get all of the marks from the diagram alone if it's clear enough. So I'm going to go ahead and do the diagram. First of all, I need to draw the main reactants, which are 3-methylpentoene and hydrogen bromide, and that's going to get me the first marks on the board. So first things first, there's this hydrogen bromide molecule approaches this electron-rich area, which is the double bond on an alkene. This is going to become slightly positive, and this is going to become slightly negative. I mean, that will have already happened because of the difference in electronegativity between the bromine atom and the hydrogen atom. And what we've got to do here, and this is going to get us our first mark, we want a curly arrow coming from the double bond because only electrons can move. Protons are stuck in a nucleus, they can never move. And we have to make that clear that that curly arrow is going to the positive hydrogen, like so. And as hydrogen only has one electron, if you imagine its box orbital, it has like one s1, so it has one electron, right? When it is bonded, like it is to bromide, then it also has an electron from bromide. There is no other way that hydrogen can accept any electrons like it is from this double bond without breaking this bond here. It has to make space to accept these two electrons. So in order to make space for these two electrons from this arrow, it has to get rid of the two electrons that it already has with the one shared from bromide. And it's going to do that by breaking this hydrogen bromide bond. Make sure you draw this curly arrow touching that bond or as close to touching as you can get, and then coming down to the bromine. You don't want the examiner to think that you're doing that. That would not get you the mark because the examiner will think you're saying the electrons are coming from the hydrogen and not the bond. Okay, there we go. So let's make sure we do that. Right, that's the first couple of marks on the board. Right there. You're showing your electrophile, this hydrogen atom with a delta positive sign, and you're showing a curly arrow from the double bond to the hydrogen and a curly arrow from the bond to the bromine. Wonderful. Now we're going to show that we can form two possible intermediates. And here are the two intermediates, and these are really important for explaining why we get a major product and why we get a minor product. So I'm going to go ahead and redraw this out. Okay, so in this first intermediate, this is known as a carbocation, and this is a special type of carbocation. Carbocations are not the carbon atom with the positive charge. A carbocation is the entire molecule, but the positive carbon on the carbocation is where my bromine is going to attack. So my bromine that has snapped off from here now has a lone pair and a negative charge. And so we need to do that. And we need to show a curly arrow attacking here. Now, what is this going to form? Well, when we draw that bromine on here, this is going to be 1, 2, 3, 4, 5 pentane, and we're going to have this is going to be 3 bromo, 3 methylpentane. So this is going to be 3 bromo, 3 methyl pentane once this is joined together from this carbocation. And this is the major product, and there's a reason why this is the major product. So, this carbo, whoa, this carbocation um, is very stable as it is a tertiary carbocation. Now, that's very important that you call it a tertiary carbocation. Of course, you can write a little three with a dot to stand for tertiary. So it's a tertiary carbocation. It has three alkyl groups, um, all electron kind of donating. They have having an inductive effect, stabilizing the plus charge on the carbon atom. So this is making um, that's a lot of waffle there, isn't it? So this essentially over here is making this molecule, this tertiary carbocation is more stable because it has, and I'm going to show you here, it has an ethyl group here, that's an alkyl group, a methyl group here, and then another CH2, CH3, another ethyl group there. And all of these are their electrons are being drawn towards this positive charge, and the electrons are cancelling out that positive charge, making this the more likely carbocation to form. And therefore, this explains why 3 bromo 3. So this explains why I've got to write that blooming thing out. That is so long. 3 bromo. Oh my good gosh. 3 methyl pentane. Um, is the major product. Okay, the key terms here. Yes, I need to show the bromine like that. Yes, I need to draw the correct carbocation like I have there. And I also need to say that this carbocation is a tertiary carbocation. Okay, and this explains why this is the major product. And I really need to compare it to the other one and say it's more stabilizing, which I could say here, but I want to draw the other one out first. And then I'm going to compare that and say that the minor product is less stabilizing. So I'm just going to go ahead and draw out the minor carbocation and therefore, which leads to the minor product. Let's go. Okay, now in the alternative version, the hydrogen atom over here that first attaches to either carbon of the double bond, obviously our single bond has broken because it has formed the bond with a hydrogen. In this version, the hydrogen atom has formed here. So I'm going to circle that. That's this hydrogen atom here. It has attached here, leaving this as the carbocation. However, this carbocation is not as stable as this one. And I'm going to explain why, and I will circle in pink. It has a methyl group attached, but it's got a hydrogen atom, which doesn't have much of a sort of positive inductive effect. It doesn't really donate those electrons. This does, this R group here, this methyl group. And then we've got this group here, is also over here, this group is also donating some electrons. So what I have over here are two R groups. You can call these R groups, alkyl groups in your answer, or and they are donating their electrons or allowing their electrons are having an inductive effect on the positive carbon atom in this carbocation. But because there's only two R groups compared to three, we call this a secondary carbocation. So what I'm going to do is I'm going to say um, here the secondary carbocation formed um, is less stable than the tertiary carbocation, as it only has two alkyl groups with an inductive effect on the carbon. Um, so this carbocation is, I think I already said this. Did I say it was less likely to form already? Is less likely to form, hence, um, 2 bromo, 3 methyl. This is why organic chemistry kills some people. It's so long-winded. Pentane is the minor product. Okay, and that should get us all of the marks. What we're doing here is just justifying why this one is less likely to form. And we're going to put the lone pair there. We're going to put a little negative sign and a curly arrow from there to there to show it attacking the positive carbon on this carbocation. Remember, the carbon atom is not the carbocation. The whole thing is the carbocation. This is the positive carbon on the carbocation. But what we really want to get the gist is that the second carbocation, this carbocation, is less likely to form because it's less stable, because it only has 2 R groups, and they each R group has a stabilizing effect on this positive carbon atom, but as it only has 2 R groups, there's less of an inductive or stabilizing effect on the positive carbon atom. And so the carbocation is less stable than this one, which has 3 R groups, which has a greater inductive effect on the positive carbocation, on the positive carbon atom. And so we're much more likely to get 3-bromo 3-methylpentane as the major product, whereas here 2-bromo 3-methylpentane is going to be the minor product. Okay, and that should get you all of the marks. So I'd expect you to get another mark for the correct secondary carbocation, and then marks for pointing out that it only has 2 alkyl groups and that the carbocation is less stable, therefore less likely to form. And that's going to get you all of the fat marks that you want for this 7 marker. All right, guys, I hope that helps. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks, smash them exams. I'll catch you on the next vid.
You're still here? It's over.